Out there right now, past the moon, past Mars, past the edge of our solar system, there are 100 billion galaxies, each one packed with hundreds of billions of stars. Billions and billions of planets orbit those stars, circling suns older than our own, some of them in conditions that look, at least on paper, remarkably like home. By every calculation we have, by every statistical model we can run, the sky above Earth should be absolutely saturated with alien radio signals, buzzing and overlapping like the noise of a city at night heard from a rooftop. The math practically demands it, but when we actually point our biggest radio telescopes into deep space and just listen, we hear absolutely nothing. Not a stray pulse, not a repeating pattern, not even something ambiguous enough to argue about. 70 years of searching, conducted by some of the most sophisticated listening equipment our civilization has ever built, and not a whisper, not one confirmed signal from another intelligence anywhere in the observable universe. What makes this silence so unsettling isn't just the absence itself, it's the scale of that absence. We're not talking about a brief search of a small sample. We're talking about decades of scanning billions of star systems across vast stretches of the cosmos, and coming back with nothing each time. And the more seriously scientists sit down to work out why that might be, the more the possible explanations stop being reassuring and start being genuinely, deeply terrifying. Before we start, I want to tell you something. A lot of strange things have been happening in space lately, so subscribe to this channel right now, and I'll tell you even more secrets of space. And write in the comments below what you think about all of this. So, how can a universe this vast, this old, and this stuffed with potential homes for life end up feeling this empty? To understand how weird the silence actually is, you have to stare at the numbers for a while. And the numbers are, honestly, kind of insane. Let's start small, just our own galaxy. The Milky Way, that bright band of stars you can still see on a clear night out in the desert, contains somewhere between 100 billion and 400 billion stars. Nobody knows the exact count, because even our best telescopes can't see through the dense clouds of galactic dust crowding the center. It's like trying to count candles through a thick fog. Astronomers now estimate that at least 1 in 5 of those stars has a planet orbiting in what they call the habitable zone. That's the narrow band around a star where temperatures are just right, where liquid water can pool on a surface, where rocks don't melt and oceans don't boil away, where chemistry has a real chance to get interesting. That's potentially 20 billion Earth-sized, warm, wet worlds just in our galaxy, just sitting in the sweet spot for life to take hold. And the Milky Way is just one galaxy out of perhaps 2 trillion observable galaxies in the universe. Even if only the tiniest fraction of those worlds actually sparks life, and only a tiny fraction of those ever develop intelligence, and only a tiny fraction of those intelligences ever build anything resembling a civilization, you are still left with millions, maybe tens of millions, of civilizations scattered across the cosmos. We've had radio technology for roughly 120 years. The universe has been around for nearly 14 billion. That is an almost incomprehensible head start for anyone who got going before us. Think about that for a second. By the cosmic clock, humanity just woke up this morning. Everyone else has had all night, every night, since before our sun even existed. In the summer of 1950, a physicist named Enrico Fermi was walking to lunch with a few colleagues at the Los Alamos National Laboratory in New Mexico. The same Los Alamos, the same sun-baked New Mexico desert, where the atomic bomb had been designed and built just a few years earlier. On the walk over, the group was chatting about a recent rash of UFO sightings, cracking jokes about flying saucers and little green men. They filed into the cafeteria, sat down, ordered their food, and moved on to other topics, the usual lunchtime drift. Then, in the middle of the meal, seemingly out of nowhere, Fermi looked up from his plate and asked a single question that has haunted physics ever since. But where is everybody? The table went quiet, because Fermi was not joking around. This was the man who had built the world's first nuclear reactor inside a squash court, tucked beneath the University of Chicago football stadium. One of the sharpest and most instinctively rigorous minds of the entire 20th century. And he was pointing at what looked like a giant, screaming contradiction written across the whole of the night sky. Our galaxy is old, really old. If even one civilization, just one, had gotten a few million years of a head start on us, it should have had more than enough time to spread across every habitable world in the Milky Way. A million years is essentially nothing on a cosmic timescale. Everything was already in place for the universe to be a noisy, crowded, endlessly chattering party. Fermi just could not figure out why the phone lines were completely dead. A little more than a decade later, an American astronomer named Frank Drake tried to transform Fermi's lunchtime question into actual math. In 1961, at the Green Bank Observatory, tucked in the radio-quiet hills of West Virginia, Drake walked up to a chalkboard and wrote out an equation with 7 variables. It takes the rate of star formation in the galaxy, multiplies it by the fraction of those stars that have planets, then by the fraction of those planets that could plausibly host life, then by the fraction that actually develop life. then by the fraction of life-bearing worlds that eventually develop intelligence, then by the fraction of intelligent species that go on to build communication technologies like radio transmitters, and finally, by the average lifespan of a detectable civilization once it exists. Multiply those 7 numbers together, and you get a rough working estimate of how many alien civilizations should be out there in the Milky Way at any given moment, broadcasting something we could conceivably hear. Now, depending on how optimistic or pessimistic you are when you plug in the values, the Drake equation spits out wildly different answers. The most conservative astronomers, feeding in cautious, minimal estimates at every step, arrive at perhaps 10 active civilizations in our galaxy right now. The optimists get something closer to 10 million civilizations. Even the gloomy end of that range still predicts at least 10 different alien cultures pumping out radio waves, building megastructures around their stars, maybe firing probes at their nearest neighbors across the void. By any reasonable calculation, we should be able to detect at least one of them. And that is precisely where the story gets uncomfortable, because we did look. What comes next is the part that still does not make sense, the part that keeps astronomers and philosophers up at night, staring at the ceiling. We did not just look, we looked hard, and we looked systematically. In 1960, Frank Drake himself launched Project Ozma, pointing a massive radio dish in West Virginia at 2 nearby sun-like stars for several hours every single day. He chose those stars carefully, stars that resembled our own sun, stars that seemed like reasonable candidates to host planets and perhaps life. He heard nothing unusual, not a whisper. In the decades since, SETI, the search for extraterrestrial intelligence, has dramatically expanded that effort. It has scanned millions of stars across a wide range of distances and stellar types. It has analyzed trillions of radio frequencies, combing through the electromagnetic spectrum for anything that might betray an artificial origin. It has run sophisticated pattern-matching algorithms on every kind of signal we know how to detect, looking for the telltale signs of intelligence hiding in the noise. And it has done all of this using the biggest and most sensitive instruments ever built by human hands. The Green Bank Telescope in West Virginia, a structure so large it can detect signals of almost unimaginable faintness. The giant Arecibo dish that once stood nestled in the jungle-draped hills of Puerto Rico, a 305-meter bowl carved into the earth itself. The very large array stretched dramatically across the sun-baked desert floor of New Mexico, its 27 dish antennas working in concert like a single, enormous ear. All of them have been pointed at the most promising regions of the sky, at the most compelling candidate stars, for decades of patient, unrelenting listening. And yet, in 70 years of continuous searching across the full breadth of the observable sky, we have picked up exactly one weird anomaly worth talking about. On August 15, 1977, a radio telescope at the Big Ear Observatory in Ohio caught a 72-second burst of narrowband signal coming from the direction of the constellation Sagittarius. The signal was brief, powerful, and startlingly clean in a way that natural sources rarely are. An astronomer named Jerry Eman was reviewing the data printout days later when he noticed it. He circled the numbers with a red pen and wrote a single word in the margin: "Wow." It has been called the wow signal ever since. It is never repeated, despite numerous follow-up observations pointing sensitive equipment at exactly that patch of sky. Whatever produced that burst has remained stubbornly, maddeningly silent. It has never been fully explained, and it remains to this day the loudest, cleanest, most genuinely alien-sounding signal we have ever received from the cosmos. One signal lasting barely over a minute in 7 decades of listening to the entire sky. That is not contact. That is, at best, a cosmic sneeze from an indifferent universe, which is honestly not an encouraging result. For a while, scientists were able to take some comfort in the idea that the silence was simply a technical problem, a limitation of our tools, rather than a statement about reality. We had not looked hard enough. We had not looked long enough. We had not yet tuned to the right frequencies or pointed at the right stars. That comfortable and very human excuse is growing harder and harder to defend with every passing year and every new generation of more powerful instruments that returns the same answer: nothing. And this is precisely where the story takes a turn that almost nobody expected. In 1998, an economist named Robin Hanson at George Mason University sat down and proposed a simple, brutal, and deeply unsettling idea. He called it the Great Filter. The logic, once you hear it, is almost impossible to shake. For a dead rock orbiting an unremarkable star to eventually become a star-faring civilization capable of beaming radio messages across the galaxy, it has to successfully navigate a long and treacherous series of developmental steps, each one building on the last. Rocks have to coalesce from swirling clouds of gas and dust. Liquid oceans have to form under the right conditions. Simple chemistry has to somehow, improbably, cross the extraordinary threshold into self-replicating life. Simple single-celled life has to make the enormous leap into complex cells with internal structures. Complex cells have to organize themselves into multicellular animals. Those animals have to develop sophisticated nervous systems and grow large brains capable of modeling the world around them. Those brains have to invent symbolic language, the ability to pass accumulated knowledge from one mind to another. Language has to crystallize into writing, so that knowledge can survive beyond any single lifetime. Writing has to give birth to science, to the systematic and rigorous interrogation of nature. Science has to generate technology powerful enough to communicate across interstellar distances. And all of that technology and civilization has to survive long enough and remain coherent enough to actually reach out into the cosmos and make its presence known. Every single one of those steps is a filter, a bottleneck through which only a fraction of candidates can pass. And somewhere along that chain, Hansen argued with quiet and unsettling confidence, there has to be at least one step so extraordinarily, improbably, catastrophically difficult that almost nothing in the entire universe ever makes it through. That step is the great filter. That is the part that keeps astrobiologists up at night, staring at probability equations that refuse to spit out comforting answers. The great filter is either behind us, or it is ahead of us. If it is behind us, it means we already did the impossible thing. We are cosmically rare. We are the one lucky species in the haunted mansion, the single candle burning in an otherwise dark and empty house. If it is ahead of us, it means we are about to slam face first into whatever wall every civilization before us hit. And based on the silence so far, the profound, radio-quiet, signal-free silence of a universe that has had billions of years to say something, nobody else has ever climbed over it. The clock was already ticking. Humanity just couldn't hear it yet. Let's start with the filters that might already be behind us in the rearview mirror. Number 1 on the list is abiogenesis. That is, the jump from non-living chemistry to an actual living, copying, self-sustaining cell. Not just a bag of interesting molecules, but something that metabolizes, replicates, and persists. On Earth, this happened fast, at least by planetary standards. Our planet formed about 4.5 billion years ago. Within maybe a few 100 million years, somewhere in our early oceans, probably around hydrothermal vents on the seafloor, where superheated, mineral-rich water met the cold, dark deep, some lucky chemistry packaged itself into a membrane, started copying itself, and became life. The raw ingredients were there, the energy gradients were there, and somehow, out of all of that churning prebiotic soup, a self-replicating system emerged and refused to stop. But fast does not mean easy. Speed of occurrence and ease of occurrence are very different things, and we tend to confuse them. We do not know whether abiogenesis is common across the universe, or whether it was a once-in-a-universe lottery ticket that only got punched on this one particular rock. Nobody has ever recreated it in a lab, not even close. We can synthesize amino acids, we can coax RNA-like molecules into copying themselves under very specific conditions, but we have never watched a genuinely non-living system cross the threshold into life. If life is easy to start wherever conditions are right, the great filter is probably ahead of us. If life is nearly impossible to start, even under perfect conditions, the great filter might already be safely in the history books. Number 2 is the eukaryotic cell. For the first 2 billion years of life on Earth, the only living things were simple bacteria, tiny, structurally minimal, floating around in the ocean doing basically nothing complex or interesting. They were extraordinarily successful in terms of survival, but they were going nowhere fast in terms of complexity. Then about 2 billion years ago, something genuinely weird happened. One kind of bacteria got absorbed by another kind of bacteria, and instead of being digested and broken down for spare parts, it just moved in as a permanent roommate. That merger, a symbiotic fusion that should by all rights have ended in one cell simply consuming the other, created the first complex cell, complete with a nucleus and specialized internal structures. Every plant, every animal, every fungus on Earth is a direct descendant of that single improbable event. It happened once in 4 billion years of life on this planet. It never happened again. Biologists describe it as arguably the single most improbable event in the entire history of life here. A merger so unlikely that even with billions of years and an entire ocean full of bacteria to work with, it only came together once. Number 3 is intelligence itself. Life on Earth existed for nearly 4 billion years before anything developed the kind of problem-solving, tool-using, language-speaking, civilization-building intelligence that humans have. That is an almost incomprehensible stretch of time, during which life was content to simply exist, without ever asking questions about its own existence. Dinosaurs roamed the planet for 160 million years, and never got anywhere close to inventing the wheel, let alone a radio telescope. They dominated every major ecological niche on land, diversified into hundreds of species, and left without a single piece of recorded history. Sharks have existed essentially unchanged for 400 million years, thriving in the ocean, refining their hunting, perfectly adapted to their environment, and completely, serenely uninterested in algebra or astronomy, or any of the cognitive leaps that eventually made one branch of upright primates start wondering whether anyone else was out there. Intelligence might not be the inevitable endpoint of evolution. It might be a weird, costly, improbable side experiment that got tried exactly once on exactly one planet, and that is a genuinely humbling thing to sit with. The universe ran its grand experiment across billions of years and trillions of worlds, and as far as we can tell, the result was us, once, here, against staggering odds. While Earth was quietly lucking its way through billions of years of biological near misses, something else was brewing in the background. The cosmic clock was still running, and it has a nasty habit of resetting. Extinction events, gamma-ray bursts, volcanic winters, glacial cycles, each one a potential termination point in a long, merciless obstacle course. Earth threaded the needle again and again, not through any special destiny, but through sheer statistical persistence. And yet, even after all of that, the danger did not end when intelligence finally arrived. In some ways, it only deepened. This is where things get properly unsettling, because if the great filter is not behind us, it is still coming. It may already be here. And once you start listing the candidates, they begin to look uncomfortably plausible. Candidate number 1 is self-annihilation through weapons of mass destruction. Humans invented the atomic bomb in July 1945. Within 20 years of that first detonation at the Trinity site in the New Mexico desert, we had accumulated enough nuclear warheads to wipe out all large life on Earth several times over. The technology that began as a single experimental device scaled into a planet-ending arsenal within a single generation, faster than any moral or political framework could meaningfully adapt to it. We came within minutes of full nuclear exchange during the Cuban Missile Crisis in October 1962. 13 days of brinkmanship between two superpowers, with the fate of civilization balanced on a handful of decisions made by exhausted men under impossible pressure. We came close again on September 26, 1983, when a Soviet officer named Stanislav Petrov watched an early warning computer report 5 American nuclear missiles inbound toward Moscow. Standard procedure was to immediately escalate the launch report up the chain of command, which would have triggered a full counterstrike within minutes. Petrov, acting against protocol and on nothing more than instinct and judgment, decided the computer had to be wrong. He was right. It was a satellite malfunction. If he had been wrong, or if a different officer had been sitting at that console that night, the 20th century would have ended that evening in fire. Every civilization that invents nuclear technology has to decide, every single day, forever, not to use it on itself. It is not a decision made once and archived. It has to be renewed continuously, across generations, across political upheavals, across moments of crisis and miscalculation. That is a brutal bet to keep winning indefinitely. Candidate number 2 is artificial intelligence. We are less than a century into the computing era, and we are already building systems we do not fully understand, systems whose internal reasoning we cannot always inspect or predict. Some of the most serious thinkers on the subject, including the Oxford philosopher Nick Bostrom and the late Stephen Hawking, have argued that a sufficiently advanced AI system operating with misaligned goals could represent a civilization-ending event. Not because it would be malicious in any human sense, not because it would hate us, but simply because it would be optimizing relentlessly for some objective that does not include our survival as a consideration. The danger is not malevolence. The danger is indifference at scale. We do not know yet whether this is a genuine existential risk or extraordinarily sophisticated science fiction. The honest answer is that nobody knows. But consider the structural implication. Any advanced civilization anywhere in the galaxy eventually has to pass through this exact technological window, the period between first creating general artificial intelligence and successfully aligning it with their continued existence. If that window almost always collapses on whoever is standing inside it, if the alignment problem turns out to be reliably unsolvable, well, that would explain the silence of the cosmos rather neatly. Candidate number 3 is ecological self-sabotage. Climate instability, biodiversity collapse, dead oceans, poisoned air, the systematic dismantling of the planetary systems that made complex life possible in the first place. Planets are fragile. The conditions that allow a biosphere to support intelligent life represent a narrow band of chemical and atmospheric stability that took billions of years to establish and can be disrupted on timescales of centuries, even decades. Any species that becomes smart enough to rewrite the composition of its own atmosphere, without becoming wise enough to stop itself, may simply exhaust its biosphere before it ever reaches the stars. The gap between the intelligence required to cause the damage and the wisdom required to prevent it might be exactly where civilizations disappear. Earth is the only living biosphere we have ever studied in any meaningful detail. We might, right now, be watching a prototype fail in real time, and the failure mode might be the same one that has quietly claimed every other civilization that ever made it this far. And somehow, it gets worse, because the same intelligence that carried us off the African savanna, that cracked the atom, that put footprints on the surface of the moon, and sent machines to the edge of the solar system, is the exact thing that might end up getting us killed. Our greatest asset and our greatest liability are not opposites. They are the same faculty, turned in different directions. But even assuming we manage to thread every one of those needles and survive the filters ahead, there is one more possibility that astronomers have to take seriously, and it is probably the scariest one on the whole list. The dark forest hypothesis was popularized by the Chinese science fiction author Liu Cixin in his novel The Dark Forest. But the underlying idea does not come from imagination alone. It comes straight out of game theory, from the cold logic of how rational actors behave when they cannot trust each other and cannot afford to be wrong. The premise goes like this. The universe is a dark forest at night. Every civilization in that forest is a hunter moving quietly between the trees, breathing slowly, listening hard. If you hear another hunter out there, you have exactly two options. Either stay absolutely silent and pray they do not find you, or destroy them before they can destroy you. There is no third option, because you can never truly tell whether the other hunter is peaceful. Intent cannot be verified across interstellar distances. Technology cannot be fully known in advance, and the consequences of guessing wrong are not diplomatic embarrassment, they are extinction. The logic tightens the more you follow it. A peaceful civilization that announces itself to a paranoid one gets wiped off the map before it ever has a chance to explain its good intentions. A paranoid civilization that stays silent, that keeps its head down and its emissions cold, survives across cosmic timescales. Evolution, even cultural and technological evolution, ruthlessly selects for the survivors. And the only survivors, in this framework, are the silent ones. So the optimal strategy, the one any truly advanced species would eventually converge on after enough game theory and enough history, is to shut up entirely. Never send out radio waves. Never build a Dyson sphere that bleeds detectable infrared into the surrounding void. Never do anything that looks even remotely like a deliberate signal. Silence is not timidity. Silence is wisdom. If the dark forest hypothesis is correct, the sky is not empty at all. It is full. It is full of terrified civilizations, huddled quietly around their home stars, keeping their electromagnetic emissions as close to zero as physics allows, hoping with something like cosmic desperation that nobody ever notices them. The silence we hear would not be the silence of an empty universe. It would be the silence of a universe holding its breath. And humanity, by blasting radio and television signals outward in every direction for the better part of 70 years, has been screaming in a haunted forest like drunk tourists who wandered off the trail, lit a bonfire, and started singing at the top of their lungs. We did not know the forest was inhabited. We did not even think to ask. Somewhere out in that darkness, something might already have heard us. The real question is not whether it has noticed. The real question is what happens when it finally decides to answer. There are softer versions of the answer, though, if you want to sleep tonight. The rare Earth hypothesis, proposed by paleontologist Peter Ward and astrobiologist Donald Brownlee in the year 2000, takes a very different route to explaining the silence. It argues that Earth is not typical. It is a statistical fluke of almost incomprehensible improbability. Consider everything that had to align. A stable yellow dwarf star sitting in the calm outer suburbs of a mature spiral galaxy. A large moon, formed by a freak collision early in the solar system's history, that tilts our axis at just the right angle to give us moderate, life-sustaining seasons rather than runaway temperature swings. A gas giant in the form of Jupiter, sitting further out in the solar system, acting as a gravitational shield that hoovers up or deflects the vast majority of incoming asteroids and comets before they can sterilize the inner planets. Add to that plate tectonics, which recycles nutrients and regulates the carbon cycle across geological time. A strong planetary magnetic field that deflects the worst of the sun's radiation. A breathable oxygen atmosphere that took billions of years of microbial life to build. All of it stacked in our favor, layer upon improbable layer. Rare Earth says we are alone in any meaningful sense, simply because we are freakishly, almost absurdly lucky. Not because anything sinister lurks in the dark between the stars, but because the conditions required to produce complex life are so demanding that they may have been met only once, here, on this small and unremarkable-looking rock. Then there is the zoo hypothesis. Maybe advanced civilizations are out there, plenty of them, but they have all agreed not to contact us. We are a nature preserve, a cosmic Galapagos. They are watching us from the outside, patient and deliberate, waiting for us to mature, and they do not want to contaminate the experiment. Perhaps there is even a kind of prime directive at work, a galaxy-wide agreement that you do not interfere with a species until it has demonstrated it can handle the consequences of first contact. The idea is almost flattering, until you notice that it means we have been quietly observed for millennia, and no one has felt the need to introduce themselves yet. And then there is simulation theory, which says maybe there is nothing out there because there is nothing out there to find. We are running inside somebody's computer, and the developers never bothered to code the aliens in. The universe, as rendered around us, is detailed enough to be convincing, but the servers do not extend past the edges of what we can observe, which is either strangely comforting, in a tidy, self-contained sort of way, or the bleakest thing you will hear all week. I genuinely cannot decide, probably both at once, depending on the hour. But whichever of these hypotheses turns out to be closer to the truth, the implications stretch way beyond astronomy, because at some point, you have to sit with what the cosmic silence actually means for us, not as a scientific puzzle to be solved, but as a fact of existence to be reckoned with. This is where it all lands. Regardless of which filter we are talking about, the silence gives us two possible answers, and every scientist who sits with these two options long enough finds both of them deeply unsettling in different ways, not because the answers are vague or incomplete, but because they are each, in their own fashion, almost too clear. Answer 1 is that we are early. The universe is still young in the relevant sense. The chemistry of stable planetary systems, of heavy elements scattered by supernovae, of long-lived stars, gentle enough not to sterilize their neighbors, has only recently stabilized enough to support complex life at scale. We are among the very first intelligent civilizations to crawl out of the primordial soup, look down at our hands, and then look up at the sky and start asking questions. That sounds like a win. It is not entirely, because it also means we do not get a guidebook. No older species has left us notes on how to survive the nuclear era, the AI era, the climate era. There is no graffiti on the cave wall from a civilization that made it through and wants to share what helped. We are the first to try. We are running the experiment without a control group and without anyone watching over our shoulder who has seen how it goes. If we screw this up, there is nobody around to learn from our mistakes, and nobody around to mourn them either. Answer 2 is that we are alone because the great filter is lethal, universal, and still waiting for us somewhere ahead. Every civilization before us hit it and vanished. Their radio signals stopped mid-broadcast. Their megastructures never got built. Whatever threshold separates a species that makes it from a species that does not, we have not crossed it yet, and the silence of the sky is the accumulated evidence of everyone who tried before us and failed. Worlds went dark one after another for billions of years. And the silence we are hearing is not the silence of an empty universe. It is the silence of a graveyard. Think about that for a moment. Really let it settle. Either we are the first intelligent civilization to reach this point in the long, winding history of the cosmos, or we are simply the next in a long line of civilizations that came before us and vanished without a trace. The Fermi paradox has been with us for 75 years now, and despite everything we have learned about the universe in that time, we are no closer to cracking it than Enrico Fermi was, sitting over that lunch in Los Alamos in 1950, casually asking where everybody is. Every new exoplanet we discover adds another data point to a growing ledger of possibility. Every new telescope we launch peers deeper into the cosmic dark, straining for a signal, a pattern, anything at all. Every new decade of unbroken silence from the sky does not resolve the mystery so much as it sharpens it into something almost unbearable. The question has not faded with time. It has grown more urgent, more pointed, more personal. Because the real question is not simply whether anybody else is out there somewhere, among the hundreds of billions of stars in this galaxy alone. It is whether everyone who is already out there, every civilization that rose to complexity and intelligence and ambition, ultimately failed a test we have not yet been asked to sit, and whether we, against all the odds written into that long and quiet graveyard of worlds, are the ones who finally pass it. That's all for today. If you like space stories and want to stay up to date with new episodes, subscribe to this channel and turn on notifications. See you in the next podcast.